Okay. Yeah, welcome to the talk with the way too long title. Template parameter packs, types, and value lists, why and how. And that's pretty much. So the agenda is we look at parameter packs, fold expression, type and value lists. And as a bonus, this is the clickbait, tiny tuple rabbit hole. Okay, so the usual disclaimer for my talks, the code I show is slideware. I try not to make errors, but can happen. Often I have personal opinions. It's okay to discuss them after the talk in the middle part. For technical stuff, I have the slide numbers here in the corner, as you see. And no universal solutions. Sometimes even if I say it is like this, there are exceptions, context, and so on. Yeah, don't mention this even. And the geek factor is probably a 3 out of 5, so it's pretty much tutorial style, but you know a little bit of C++. Yes, and if you don't know who am I, this is me. The private profile and the public profile, it's basically the same because I try always to be authentic. So the preamble variadic templates, what are they and why are they useful? And just to note that what we're talking about, to bring us all at the same, we know state variant, so it can hold one of the values we specify. We know the print function, the new one, which is awesome, right? It takes the formatted string, and then however, how many arguments you need. Or we have the tuple, which is basically a list of types that creates a data structure for you on the fly. And variadic templates are classes or function templates that take a template parameter pack. Okay, so now we have the first thing, template parameter pack. It restricts possible options, like in the case of the variant, hold one off, or call with one off, what we will see later. Or it gives us whatever option, create a function with all of those from this domain, and we take whatever. And how do they look in the implementation? We can have them explicit declared as the template stuff with the ... and then having here the function. Or in modern C++, we can also let the compiler deduce the types, and we just write auto, which is convenient. For types, we of course have to specify the argument pack. So that's how it is, and then we can use it, join, we put in whatever we do, or for the type, we declare the type with the types we want. That's the usage. I don't think there are very many surprises for you. Variadic arguments looks like this, the template parameter pack, and the template argument pack when we use it. And if I say the wrong thing, at least I told you what the right things is now for them things to name. Okay, so using a template parameter pack, this is what we want, the join function. And I specified the function, it takes one or as many arguments as they want. And if we put them in, it joins the input with the comma and put them together as a string. So how does this look? So pre-C++ 17, it looked pretty wild. So we had the user interface, this join function, which takes 1 or 0 to whatever arguments. And then you had the preparation of the implementation detail. The implementation detail happens here. In older code, you see this a lot, that you recurse over the arguments with a head and a tail. You do whatever you need to do with the head. If there is a tail, you continue with the tail, you recurse into it, you put the tail in, the head will be popped up, and the rest goes into here. Once this is empty, this terminates, and the join function is done, and it can return whatever it does. So since C++ 17, we can do it like this. And that's called the unarray right fold over the comma operator, which is an awesome statement to intimidate junior developers. But we don't want to do this, so we will look into this, what this actually is, because it's pretty simple. So let's look into fold expression, because this is. Oops. So a fold expression is one of unarray left fold, unarray right fold, a binary left fold, or a binary right fold. And then you need a binary operator that takes two things. And this is the technical list of those that you can use. Most of them don't make sense in reality. The arithmetic ones make sense. And then the comma operator is interesting. That makes a lot of sense. By the way, if you want to see a talk about the comma operator, there is one on the Sweden CPP YouTube channel where we talk about the comma operator, having fun with it. Then the and or is also, but we have a function for those in the standard library. We will see them. This is what mostly is used, but let's look into the practical part. So I have a left fold and a right fold, and I use the subtraction. And to showcase this, I use the same values that I pass in. And the left fold returns me -8, and the right fold returns me -2. So now, why is this? This is because associativity matters sometimes. And in the left fold, you go from left to right. 1, -2, -3, -4 is -8. In the right fold, you have the 3 minus 4 is -1. 2 minus -1 is 3, and 1 minus 3 is the -2 that we get. So the terminology of left fold and right fold is basically how you unroll the arguments. And now let's have a look at the unarray for a binary fold. So this is now a left fold of the plus operator. If I call this with no argument, I will get a pretty nice error message that is really helpful. Empty expansion over the operator plus, and shows me where it is. So I cannot do this with the plus operator. For being able to have this with the plus operator, I need the identity element, which is the 0. And now if I call add with no arguments, I get 0, what is what I expect, and the compiler will be happy. So now bringing this together, we have the binary function, we have the unarray fold. So here you have the castable expression where the compiler says, okay, this is a statement, it has the value. Here it has the expansion. We can now use the empty stuff for the binary fold. And for the unary fold, if you have nothing, the type is void. And in this time, in this scenario, the compiler finds it out with the comma operator. I just do nothing. And that's how unarray and binary fold left and right works. And you can put it together on a simple cheat sheet like this. And now there should be no surprises anymore. It's very confusing when you see the code first time in the level, what's going on? But now you see, okay, we went from recursion to the fold expression. If you know these things, it's pretty basic to figure out what the code does, and it becomes readable. Now C++26 will even help us more and make the things even more readable. So one of the nice things we will get is unpacking the tuple elements into structured binding. And Paul did the talk about structured binding. It's on the YouTube channel, Sweden CPP, of course, if you want to know more about this. But that's pretty convenient. And we have an index access. This is also will make it very nice to use the argument packs. And then what I recently saw was a compile time for loop, which makes the code then look like normal code. And that's beautiful, because if you see, right, we started with this recursion where you needed to know how to do and the details. Then we got to the fold expression, which is a little bit exotic. And now the code looks like everyday code. And this is what we're doing in C++, right? We cannot break the old stuff, but we can make it simpler, simpler, simpler. What you need to know, what we also had in the quiz, you need to know about these nice little things that make your day-to-day life easier. And there is already a GCC implementation where you can actually compile and run this code. So that will be awesome when this comes. So let's look into type lists. So what are type lists? Well, list of types. So let me make here an implementation. I have a type list that takes a list of types, and all it does, we have an include function that checks that the type I give for the include is part of the types I want here. And this is the disjunction, which does basically the expansion over the OR operator. And why is this useful? So check this, where we have a channel, and I define a channel with a list of allowed types. I have a sender. You can send in whatever, but this whatever needs to be included in the types of the allowed types. If not, the code will not compile. Simple as that. If the type is here, you can send it. And we will look at the receiver in a moment. Just first we call this stuff. So we define a channel with a signed char, short, and int. Does anybody know why we have a signed char?
Because it's implementation defined, whether it's signed or unsigned.
Okay, you come to me because it,
RPC or so.
exactly, there is a char is something different. So you get a JetBrains license. Okay, so we define the channel. We explicit with the type. We define the sender. If I send in double value, it will not compile. The error message is actually pretty helpful, right? Static assertion failed due to the requirement, type list, blah, 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 includes. I think this is pretty readable. I don't know why people fear the C++ compiler. I mean, of course, you need to find it. But yeah, and if you send in a list of the type list, it just works. Okay? So now let's look at the receiving part. And here, I don't do this very often, but I think I borrow here a technique from object-oriented programming. I define an abstract interface with the call operator. So that does basically nothing, but it takes a type. It returns the type and takes a type here for the selection purpose. And the usage of this is that oh my God, multiple inheritance. yeah, but we do it, right? So I expand the inheritance. I get for every type, I inherit the call operator. This receiver is still highly useless because it's totally abstract, doesn't do anything useful by its own, but I can make it useful. So if I define my channel for the types, if I don't implement one of those, I will have an incomplete type. The code will not compile. So it's clear I have to implement them. And the override is important, because if I remove or change a type, the override will be my guarantee that, hey, you override something that doesn't exist anymore. And now you have a receiver. If you have receive something, you should have a protocol. Now this type comes. Then you select these types by just specifying the type, but no value, just getting the right function call. And yeah, it's no surprise in how you use this, right? You define the receiver, and then you just say, hey, something, do the right thing, because your protocol will tell you which type you want to read. So put this all together. You define the channel. In bigger companies, right, this can be by team A that defines the channel, and team B implements the sender, and team C the receiving part. And if something here changes that doesn't fit, code will stop compiling, and you have application lifecycle management built in your compiling stuff. And I think it's pretty simple, and this is what I like. Beautiful. So, pretty useful sometimes when you need it. Now look at value lists. Okay, so what are value lists? Okay, so we do a little bit of preamble again. So non-type template parameters, NTTPs. And we all know what this is because we had two talks that mentioned them. The one is when I talked about exceptions, 2019, and then Björn Faller did a talk 2023, which also includes the new stuff, where it goes into the detail of these NTTPs. But the short reminder, we turn whatever value we want into a type. So here I turn the value 1 and the value 2 into real types. And then I can use them, overload whatever. They are types now. They are constant types. So it's cool. So this is what we do. So now I can do it with one. Can I do it with multiple? That's the question, right? But I have another question for you. Do we have in the standard library something that uses non-template type parameters? Or is it a trick question? We have nothing. No, it doesn't take non-template template parameter. It doesn't take values as argument. The array okay, yeah, you're right. Okay, it takes the size. Okay, good. JetBrains license. But that's not the answer I have on the slide. But he's right, it's array. But as we've seen in the quiz, we do array, right? No, but you're right. One more?
Index list.
Yeah. But this is such a strange thing. It's basically interesting implementation, yeah? Cool, I learned something. I need to look into this, what it really is. Because I've looked at the implementation, it's very interesting. Well, actually, I had this one, stat ratio. So we have, since C++11, we have all these aliases for the types. And there are way more names with way bigger or smaller numbers that I don't understand. But they use already 2, and 2 is a list. So obviously we can use more arguments for the value lists and turning them into types. Now, why would I ever do this? So let me give you a somewhat synthetic example that I needed to abstract a little bit, but it's not totally artificial. It actually there is code I have. So I define a type, and I take from the type whatever, how many you give me, types, okay? And what I do is I just push these things into an array, and then a shortcut to get the size of the array, and then I have the index of a value. Where is it in this array? So if I do this, I can do additional stuff. I needed to split it to fit on a slide, so I can make it, hey, I want the values you give me unique and sorted, and let me define an int list that defines the type, but I take whatever ints you give me, as long as they're unique and sorted. So now, where would I use this? Think about a grid. Okay, 2D axis, x-axis and y-axis. And I put all the data into one array, because I can calculate the size, and I can access the index. And what I can then do is I make my lists, and I make my grid, and I have now my grid as a type. And since this grid knows its type and its dimensions, it's very nice to have a large grid, a small grid, and transpose things from one place to another place. You can do it at compile time, at runtime. And usually you don't have ints in the stuff, you have something like cells. And the cells can be a strong type, which back refers to the grid it is, then it knows everything it needs to know about the universe of where it is. So, and that's pretty interesting. And I have a homework for you. You build a maze, a compile time maze, and I help you a little bit. You just need to make a quarter of it, and then you mirror it. And that's fun. Yeah. Yeah, it's not your everyday tool, value lists, but when you use them and you have a usage for them, then they're extremely useful. And you can also make fun stuff, right? Who can make a backpack game at compile time, right? Yeah, okay. So now the bonus tuples, the tuple. So why I talk about type and value lists? Why do we come to tuple? Well, because a tuple is exactly what it is. A type and a value list. This is very common. You see something like this. I take a lot of types and a lot of values, and then I create on the fly the tuple out of it. And now it is. And then I can access it like this. And it's a totally compile time stuff, right? It's not so much used in runtime. It's, hey, a function returns 2 things, and I take them and apply them to another function that takes 2 arguments, so I take this and put it in an array and 2 things together, but you rarely see them in runtime stuff. So this is the usual interface you have. Runtime usage is not so much part of the interface, but what if you would need it? Okay, now let's give me another example that is a little bit synthetic, but not far from reality. Let's say we have a grid like this, and I know in the first position I have just 1 cell, second 2 cells, 3, and you get it, right? So how would I implement this? Now, vector of vectors, or I do something with this, right? That's the first solution someone would do. And it's possible, and it works, and it's nice, but you need to all these range checks, and it's code, and it's, whoa, yeah. So I don't want to write this code anymore. So, or you make one storage, and you make a number game out of it. Then you have all constant calculations when you come to the index, you find your style, or you just define the whole thing as a type. And the type looks like this. That's exactly what you see here. It's a tuple that takes one type. It's first an array with one element, an array with two elements, an array with three elements, and all of a sudden I have my grid as a type. That's simple. That's what I want. It's also natural, right? Give me the third element on the fifth position. That's exactly what I want to say. It's captured in the type. But what if I wanted to have this a little bit of runtime access, right? Print this column at the index 5. All we have is a compile time access. That's not fair. So we need to write code. And it looks like this. So we do our tuple visit call that takes a tuple and the index that we have, and then we take a function. This function takes the right argument for what I expect. Otherwise, you will get ugly compiler messages. But you could put concepts already on this that you get better compiler messages. Anyhow, what we do a recursion. We start with 0. As soon as we hit the index, we invoke the function with the tuple. And then I can make things at runtime. Oh, can it? Yeah, thanks a lot for saving the TV. So if we're not here, we do the recursion. We have a little bit of a check that we don't go outside of the range of the tuple and land in undefined behavior. And then recurs into us with the next one. We start with 0. Now we start with 1, with 2, and with 3, and so on. And what it is, how it looks like, we have the grid. And I get the second element, and then I assign my coordinates to it. And then I say the tuple visit, grid. I want the second one. I put my function. Everything is auto. So it will work for all the arrays in the things. It will print all the arrays because auto is so beautiful. This is the usage of auto. It's not auto something different. This is where you omit the type and then you ask what do I get. But this is where auto is really the star. And then you print this by runtime. And there are other ways to do this. One of this is by Anton Williams. And the overload from journal 25. It is what it basically does. It takes the tuple, gets the addresses, it's compiled and makes a jump table, and jumps then when you by the index to the right location, you get the stuff. But this doesn't fit on 2 slides. But you can look it up if you want. So yeah. And I would like to have a runtime interface in the standard library because then I don't need to think myself about this because I like to keep it simple. OK. So now let's look a little bit into a bonus, what I have here. Everything can be a tuple when it's implemented tuple protocol. What's a tuple protocol? Are we now in Swift? No, but we have it implicit, right, since we have concepts. So the protocol is basically the tuple size. I can access the tuple element. And I have a get method. The first two are really in the stats namespace. The get not, we will see how it is. But let's make an example, then it's better understandable. I take a point for this with the int and the tuple value. And I implement the tuple size for the point by inheriting the integral constants 2. The tuple element specialization for the 0 element, so the index is an integer, and the first one is a tuple. There are other ways to implement this, but this I think is nice readable. And then we have the get method. The get method is not part of the in STD. It needs to be in the same namespace where the point is. So this is, as you see in stat, that the argument dependent lookup works. You need to be in the same namespace as the point is, but you make this getter. And the tackle type auto is to not throw away the reference, because if you give it a reference, you want to be able to assign what you get back directly. You want to say get to tuple equals, like I did it on the grid with the array. And then you have the const expression where you go by the index and you just return the stuff in brackets to not get rid of references. And you need to overload this for the const and the hourly reference. And interestingly, if you look at the tuple or the get method for the standard library, they have the const hourly reference. Because sometimes the type turns into this, and then you want to have the optimize for this. But if you implement this, you have your point as a tuple, and this is what you can do. You define your thing, and you can access this like a tuple with the structured unbinding and so on. And why would you ever use this? I don't give you everything, but there are people that find it handy. There are 2 papers that suggest the tuple protocol for C-style arrays and the tuple protocol for state complex, which is also just 2 elements. There you have the motivations, and so if you're really interested, it's a little bit exotic, that's why I have it as a bonus. And yeah, the summary already, variadic templates, type list and value lists, they solve problems for everyday usage. So you use them quite a lot. It's nothing you implement. It's not in the toolbox of the everyday C++. It's definitely library stuff that some people do. And with modern C++ and tool, it's pretty comfortable to implement. You have seen it gets more and more the compile-time programming like standard C++ code that everybody can read. And tuples are interesting, and C++ 26 will be exciting. I'm looking forward. And that's already from my side. I hope you learned something. Thanks a lot for listening.